Hi, my name is Anna Liu, and this is my lab report for lab number 5, which I chose to be analyzing the motion of a falling slinky. And the purpose of this lab is to predict the motion of a falling slinky through the usage of a computational model. And the overall goal is to determine whether or not the bottom of the slinky remains stationary whilst being dropped. And spoiler alert, it basically does. First off, there are three main equations that need to be understood for this experiment, the first of which being the drag equation, which is used to represent the air resistance onto the slinky, and this falls in line with Newton's third law, which states that for every action there's an equal and opposite reaction. The next equation is the fundamental formula, force equals mass times acceleration, which is also known as Newton's second law. And this equation is used to calculate the net force on the system, which is the slinky, as it is falling. And finally, the third equation is the gravity equation, which is used to calculate and approximate Earth's gravity acting on the slinky, which plays a crucial role in this experiment. And now that we understand more about the physics behind the lab, the next step was to collect the observational data points, which was done through the usage of Tracker. In this situation, the system would be the bottom of the slinky, and the surroundings would be the air, the earth, and the rest of the slinky. Furthermore, to assume that there are no other forces acting on the slinky, only frames 174 through 648 were used, as during those frames the hand is no longer applying a force to the system. Furthermore, the starting position was taken and recorded from the observed tracker data. And then after plotting each position point by hand, the data was then copied and pasted into a Google Sheets to be used for comparison. Next, the predicted data was created and collected through the usage of GlowScript, and I personally edited the starter code that was provided to us for lab number 2. And as seen in this slide, I edited the mass of the ball, which in this case, rather than ball, it would be the slinky, as well as editing the initial position vector of the data, which was, as mentioned beforehand, taken from Tracker. And then I also set the ball's initial velocity equal to 0, as the slinky was dropped from rest. And furthermore, the B constant that was used in the drag force equation, this value was obtained through trial and error. Next is the first while loop for my code, which represents the time in which the bottom of the slinky remains stationary, and where the slinky is still stretched out. And I edited the time constraint to fit my tracker observed data, which means that for around the first 5-ish seconds, the bottom of the slinky did remain stationary as the slinky was falling. And then afterwards, I calculated the W variable, which was just the gravity equation that was shown in the first slide. Then I calculated the tension force that the slinky was exerting, which was just the same magnitude as the gravitational force, but in the opposite direction. Then by taking the sum of the two forces, I was then able to calculate the net force acting on the slinky system. And finally, I put in the equations to calculate for the new velocity and the new position of the slinky, both of which were derived from Newton's second law. Then, for my second while loop, this represents the time in which the bottom of the slinky is no longer stationary and is now physically falling towards the earth, which was around the last 2 seconds of the tracker video. I then kept the same equation that calculated for gravitational force. However, this time, instead of calculating for tension force, I instead calculated for the drag force that the surrounding air was exerting on the falling slinky bottom. And this is because there's no longer any tension force acting on the slinky, as the slinky has been fully compressed and now it is falling as a whole object. And the drag force calculation is just the same equation that I showed on the first slide, and using the same B constant that I showed on the next slide. And next, I calculate the net force acting on the slinky by adding together the gravitational and drag forces. And finally, just like with the other while loop, I included the equations to solve for the updated velocity and position points of the system. And once I consolidated the data from both Tracker and GlowScript, I was able to create this graph that you see here. As indicated by my graph, the computational model was pretty accurate to the actually observed data of the slinky. However, there are still some small inconsistencies in the model versus the observed positional data, and this is most likely due to either human error, as I hand plotted the center of the system for every frame, or it could also be due to the slight variations in the path of the falling slinky. Now, what does it mean? Why does the bottom of the slinky stay stationary, and what does that mean? Well, simply put, because the bottom of the slinky remains stationary until it is fully compressed, that means that the net force in the y direction is equal to 0. And this basically means that the gravitational force from the earth is cancelled out by the spring/tension force from the slinky itself. So they basically have the same magnitudes, but are acting in opposite directions. And now we have the what if. What if we attach an object to the bottom of the slinky? Will the base of the slinky still remain stationary? Well, this depends on the mass of the object as well as the length and the stiffness of the spring. In order for the bottom of the slinky to remain stationary, either the length, stiffness, or both attributes of the slinky must be great enough to create a tension force that's equal in magnitude and opposite in direction to the gravitational force. Thank you for listening.